Everything in the universe is in motion, our planet rotates, the sun orbits the center of the galaxy, and even our galaxy itself hurtles through space at incredible speeds. But motion does not stop there. The fabric of the universe itself is stretching, carrying galaxies farther and farther apart. If nothing is truly stationary, a natural question arises: where is all of this heading? It is a long story, so let us begin the journey into the dream. Before we start, don't forget to like and share. For thousands of years, humanity believed the heavens were static, eternal, and unchanging. Today, we know the truth is quite the opposite. Some galaxies have already drifted forever beyond our reach. Let us delve into one of the deepest mysteries in science and discuss what we know about the ultimate fate of all things. For a long time, the universe was imagined as stable and motionless. From Earth's perspective, the stars seemed to return to the same positions every night, and constellations appeared fixed, like a giant, unchanging map across the sky. This created a sense that the firmament was eternal, locked in place without change. Even as telescopes began to reveal new wonders, most astronomers from the 19th to the early 20th century assumed the universe was static, that stars and nebulae were fixed, and that motion on the grandest scale, the drifting of entire galaxies through space, was simply not part of the picture. The first crack in this static worldview appeared through the study of light. Astronomers learned that when light passes through a prism, it breaks into a spectrum of colors, revealing alternating dark and bright lines. These spectral lines act like fingerprints, showing the chemical composition of stars and gases. But they also hide another secret: when a celestial body moves toward or away from us, the positions of these lines shift slightly. This effect, known as the Doppler shift, means that light carries clues about motion. If a star or galaxy is moving, its light will tell us. In the early 20th century, a few astronomers began applying this method to the strange spiral nebulae. At the time, whether these spirals were gas clouds within the Milky Way or island universes, vast stellar systems far beyond our own, was a subject of fierce debate. Vesto Slipher, working at the Lowell Observatory in Arizona, was among the first to notice something unusual. Starting around 1912, Slipher pointed his telescope at these spiral nebulae and measured their spectra. He expected to see random shifts, some moving toward us, some away, as one would expect from objects drifting through space. Instead, the results were shocking. Almost all the spirals he measured showed a shift toward the red end of the spectrum, meaning they were receding from Earth, often at speeds of hundreds of kilometers per second, far faster than any stars within the Milky Way. Slipher's work was meticulous but did not immediately gain widespread attention. He had no clear explanation for what he saw, but the data continued to grow. If these spirals were part of our galaxy, their speeds made no sense. If they were independent galaxies, then the universe was far more dynamic than anyone had imagined. The static universe was beginning to feel restless. In the 1920s, Edwin Hubble used the 100-inch Hooker telescope, the most powerful of its time, to achieve a breakthrough that settled the island universe debate. By studying Cepheid variables in spiral nebulae, he determined their distances and proved they were far beyond the Milky Way. The universe suddenly became much larger than previously thought. With this new sense of scale, Slipher's strange velocity measurements took on a whole new meaning. Galaxies were not just sitting in space, they were moving. The universe was not a fixed stage but an active field, with galaxies surging away like flowing water. This idea was so radical that even Albert Einstein initially resisted it. When building the equations for general relativity, Einstein found that the mathematics suggested a universe that must either expand or contract. Uncomfortable with this, he introduced the cosmological constant to force his model into a state of static balance. Yet, the light from distant galaxies could not be silenced. Most galaxies showed a redshift, and the farther they were, the greater that redshift became. Galaxies were not just moving, their motion followed a pattern. The universe itself was stretching, carrying galaxies away like raisins in rising bread dough. For centuries, measuring cosmic distances was an insurmountable challenge. Hubble solved this with Cepheid variables, stars whose brightness pulses in a way directly related to their intrinsic luminosity. By measuring the period of these pulses, astronomers could determine a star's true brightness. Comparing this to its observed brightness from Earth allowed them to calculate its distance. It was like finding a cosmic ruler in the sky. Hubble found that some nebulae were millions of light-years away, expanding the known universe to an unimaginable scale. He then compared these distances with the recession speeds measured by Slipher. The data revealed a revolutionary law: the farther a galaxy is, the faster it recedes. Einstein later called his cosmological constant his greatest mistake after seeing Hubble's evidence. For theologians, this hinted at a moment of creation. For physicists, it demanded new theories to describe the origin and fate of the cosmos. It is crucial to distinguish between motion through space and the expansion of space. In our daily lives, we understand motion as objects moving across a fixed stage. In cosmic expansion, the stage itself is stretching. There is no center point from which everything is rushing away, rather, expansion is happening everywhere. Within galaxies, gravity is strong enough to resist the stretching, holding stars and planets together. This is why the Milky Way is not being torn apart, and why we are actually moving toward the Andromeda Galaxy. Expansion only dominates on the largest scales, in the vast voids between galaxy clusters where gravity is too weak to hold the fabric together. Galaxies are like raisins in the dough. The raisins themselves don't grow, but the space between them increases as the dough rises. This leads to some extraordinary consequences. If you look far enough, the expansion of space can cause galaxies to recede at an apparent speed exceeding the speed of light. This does not violate the universal speed limit because the galaxies aren't moving through space that fast. Rather, the space between us and them is growing so quickly that their light can never reach us. This creates a cosmological horizon, leaving parts of the universe forever beyond our sight, no matter how powerful our telescopes become. This realization birthed the idea of the Big Bang. If space is stretching now, it must have been smaller in the past. Reversing the clock leads back to a single, infinitesimally small, hot, and dense origin. Long before telescopes revealed distant galaxies, the universe carried a memory of its beginning, written in light. Stretched thin by billions of years of expansion, this faint glow bathes the entire cosmos. This is the cosmic microwave background, CMB, the afterglow of the universe from a time when everything was still hot, dense, and tightly packed. It remains the most powerful evidence that the universe has been expanding since its very first moments. To understand the profound significance of the cosmic dawn, imagine the universe in its infancy. In the initial moments after the Big Bang, the cosmos was an incredibly hot, dense soup of particles and light. Photons could not travel freely, they were constantly scattered by charged particles, much like light struggling to penetrate a dense fog. The universe was opaque, glowing with its own internal heat, but any traveler within it would have been blinded. For hundreds of thousands of years, this roiling, luminous plasma held light in a tight embrace. But as the universe stretched, it began to cool. Expansion eventually thinned this dense plasma. Roughly 380,000 years after the beginning, the temperature dropped enough for electrons and protons to combine into neutral atoms, a moment known as recombination. Suddenly, light was free to travel. It no longer collided endlessly with particles but streamed outward, saturating the universe in a sea of radiation. That light has been traveling ever since, stretched by the continuous expansion of space into the microwave spectrum. When we tune our instruments today, we still capture this faint afterglow arriving from every direction. The discovery of this background radiation in 1965 was accidental. Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, struggled to eliminate a mysterious noise in their measurements. No matter what they did, even cleaning pigeon droppings from the antenna, the signal persisted, coming from every part of the sky. They had inadvertently stumbled upon the primordial glow of the universe. This discovery confirmed what Hubble's redshift had first suggested: the universe expanded from a hotter, denser state. It provided a snapshot of the universe at just a few 100,000 years old. When satellites like WMAP and Planck mapped the cosmic microwave background, CMB, with greater precision, they revealed a startling truth: the radiation is almost perfectly uniform, but not entirely. There are tiny fluctuations, temperature variations of only 1 part in 100,000. These minute differences were the seeds of all future structures. The slightly warmer spots eventually collapsed under gravity to form galaxies and clusters, while the cooler spots became vast cosmic voids. Within these subtle textures lies the fingerprint of a moving universe, already shaping the grand architecture we see today. The CMB also gave astronomers something they never had before: a frame of reference. In the vastness of space, motion is usually relative. However, the CMB provides a cosmic backdrop, a sort of universal rest frame. By comparing the glow in different directions, scientists can see that our galaxy, and indeed our entire local group, is moving relative to this ancient light at hundreds of kilometers per second. The CMB is like a cosmic baby photo, a frozen light carrying imprints from long before the first stars were born. It confirms that expansion has been occurring since the earliest moments and that the laws of physics have remained reliable. While the CMB confirmed the history of expansion, a deeper question remained: how has it changed over time? Gravity from every galaxy and cluster should, theoretically, have slowed the expansion down over billions of years. Astronomers expected that with enough precision, they would see the weight of all matter acting as a brake. But the late 1990s brought a shocking answer. Two independent teams, using Type Ia supernovae as standard candles to measure vast distances, found that the expansion of the universe is not slowing down, it is accelerating. Galaxies are being pushed apart by an invisible force, flying away faster and faster as time goes on. To explain this, astronomers resurrected an old concept: the cosmological constant. This mysterious force, now known as dark energy, appears to be a property of space itself. Unlike matter or radiation, dark energy is not diluted as space expands; its influence only grows stronger as the universe ages. Dark energy now accounts for approximately 70% of the total content of the universe. If it continues to dominate, galaxies will eventually drift so far apart that the night sky will become empty, leaving future observers in a lonely, dark universe, unaware of the grand cosmos that once surrounded them. In more extreme scenarios, if dark energy increases in strength, it could eventually tear apart galaxies, stars, and even atoms, a fate known as the Big Rip. Beyond the light of distant galaxies lies the observable universe, a boundary defined by the speed of light and the age of the cosmos. Beyond this horizon, space continues to stretch, but its contents are forever hidden from us. We often assume that the unseen parts of the universe are similar to what we see, a principle known as the cosmological principle. However, theories like cosmic inflation suggest that our observable bubble might be just one tiny patch on an unimaginably vast, or even infinite, tapestry. Some scientists even propose a multiverse, where our universe is just one of many, each with its own physical laws and history. The boundary of the observable universe is not a physical wall, but a horizon of knowledge, marking the limits of what we can ever truly know. This is a bold and controversial perspective, extending far beyond current observations, yet it is the natural extension of the theory of cosmic inflation. It suggests that the creation of space may continue indefinitely, birthing new universes beyond our touch. We live on a small planet orbiting an ordinary star, within one of billions of galaxies, and this entire universe itself might be merely a fragment of a larger structure we will never fully perceive. Our perspective is inherently limited. No matter how advanced our instruments become, there is a boundary to how far we can see. What lies beyond the horizon may remain forever uncertain. This is, in many ways, the ultimate horizon. Yet, by following the clues within our reach, pushing our observations further, and refining our theories, we continue to test these limits. With every step, the unseen realm becomes a little more concrete. When the idea of dark energy first emerged, it was not easily accepted. The discovery that distant supernovae were dimmer than expected was so shocking that many suspected an error. Perhaps the stars were obscured by dust, or the brightness measurements were flawed. To trust such a radical view, scientists needed multiple independent lines of evidence to converge on the same singular conclusion. Over the years, these proofs began to pile up. One of the most critical confirmations came from the cosmic microwave background, CMB. If the universe contained only matter and no dark energy, the size and shape of the ripples on the CMB map would look vastly different. When scientists compared actual CMB data with theoretical models, the pieces only fit if a component of mysterious energy driving accelerated expansion was included. This was an entirely independent method, separate from exploding stars, yet it pointed to the same answer. Further evidence came from the clustering of galaxies. Galaxies are not scattered randomly, they form filaments, clusters, and a vast web spanning hundreds of millions of light years. The way these structures form depends on the expansion rate. If expansion were slower, gravity would have more time to pull matter together into denser clumps. If faster, matter would be pulled apart before gravity could act. By mapping these large-scale distributions, astronomers discovered another special signature, baryon-acoustic oscillations, BAO. These are like frozen sound waves from the early universe. Before atoms formed, matter and light were tightly coupled in a hot, dense plasma where pressure waves rippled through, much like sound traveling through air. When the universe cooled and atoms formed, these ripples left a preferred spacing in the distribution of galaxies, acting as a cosmic standard ruler to measure how the universe grew across different eras. Together, these clues paint an undeniable picture. Dark energy cannot be detected directly, it reveals itself only through the stretching of space. We cannot bottle it or recreate it in a lab, but its fingerprints are written across the cosmos. This extraordinary convergence of evidence makes dark energy one of the most robust cases in modern science. Every testimony, independent of the others, tells the same story. When Einstein proposed general relativity, he rewrote gravity not as a force of attraction, but as the curvature of space-time. However, applying his equations to the entire universe led to a troubling result. The mathematics suggested the universe could not remain perfectly static. To avoid this, He added the cosmological constant, often discussed today as vacuum energy. In quantum physics, a vacuum is not truly empty. Even in regions devoid of matter, quantum fields fluctuate, with particles and antiparticles appearing and disappearing in an instant. Theoretically, these fluctuations contribute a baseline energy density to space itself. The cosmological constant represents this fixed energy density embedded in the fabric of space-time. Unlike matter, which thins out as space grows, the strength of the cosmological constant remains the same per unit volume. As space increases, the total amount of vacuum energy grows, eventually allowing its repulsive effect to dominate. However, a massive problem arises when physicists use quantum theory to calculate the predicted value of vacuum energy. The result is staggering orders of magnitude higher than what we actually observe. If that value were real, the universe would have been ripped apart instantly. This mismatch is often called the worst theoretical prediction in the history of science. It leaves us with a difficult question: is vacuum energy truly the source of acceleration? Or is our understanding of quantum fields incomplete? What if the force accelerating the universe is not frozen in time but evolves as the universe changes? This is the concept of quintessence. Named after the fifth element of ancient philosophy, it describes a dynamic, changing form of dark energy. The idea is that dark energy might come from a field similar to the Higgs field that spans the cosmos and changes slowly over billions of years. Unlike the cosmological constant, the strength of a quintessence field could increase or decrease. If dark energy is truly constant, the end of the universe is clear: eternal expansion until every star burns out and the sky is empty. But if quintessence is real, the story becomes unpredictable. If dark energy weakens, gravity might regain control, slowing the expansion or even reversing it into a big crunch. Conversely, if it strengthens, it could lead to a big rip. The big rip scenario stems from phantom energy, an even more potent form of dark energy. In this scenario, the rate of expansion increases toward infinity. Eventually, the repulsion grows faster than gravity's ability to hold matter together. It would overcome the universe scale by scale. First, galaxy clusters would be pulled apart, then individual galaxies, then solar systems, and finally stars, planets, and even atoms. In the final moments, the very fabric of space would disintegrate, and the laws of physics would fail. This would be a long, slow build-up toward a total dissolution of structure. Whether this happens depends on the equation of state parameter for dark energy. If this value is even slightly less than -1, the big rip becomes inevitable. Finally, some suggest a different path: modified gravity. This approach shifts the focus away from dark energy and instead considers that our theory of gravity might be incomplete. Just as Newton's gravity was replaced by Einstein's when we look deeper into the cosmos, perhaps we are on the verge of another revolution in our understanding of the fundamental forces. Perhaps general relativity itself is merely an approximation of a more fundamental underlying theory. While this idea seems radical, the history of physics suggests it is entirely possible. Physics has been rewritten before, and the root of the problem often lies in the question of scale. General relativity has repeatedly passed tests in environments of strong gravity, but cosmic acceleration manifests in the realm of the weakest gravity, spanning scales of billions of light-years that no laboratory can replicate. Under such conditions, it is entirely possible that when gravity is stretched to a cosmic scale, its behavior deviates from how it performs in our local neighborhood. If this is true, the strange inference we call dark energy might not be an extra ingredient the universe requires, but rather a symptom of a slight flaw in our gravitational recipe. Point 1. Early concept is known as $F(r), dollar gravity. In Einstein's equations, the geometry of space-time is described by the Ricci scalar, $r$. In general relativity, the equations depend linearly on $r$. Modified theories suggest that this dependence could be more complex, perhaps involving higher powers of $r$ or entirely different functions. While these changes appear subtle on paper, their consequences on a cosmic scale can be monumental. In certain versions, the universe would naturally begin to accelerate in its later stages without the need for dark energy. Another famous modification is MOND, modified Newtonian dynamics, originally proposed to explain the anomalous motion of stars in galaxies without invoking dark matter. While MOND is not typically used to explain cosmic acceleration, it paved the way for the argument that these phenomena might be signs of an incomplete theory of gravity. Building on this, some physicists have proposed entirely new frameworks, such as scalar tensor theories. In these models, gravity is not transmitted solely by the curvature of space-time as Einstein proposed, but is also carried by an additional field permeating the universe. On large scales, this field can act repulsively, driving expansion. In other words, rather than assuming dark energy is an independent ingredient, acceleration emerges from the way gravity itself operates. Observationally, these alternative theories must walk a tightrope. They must reproduce all the local successes of general relativity while diverging only on cosmic scales. For instance, we observe the orbital decay of binary pulsars due to gravitational wave radiation, which aligns perfectly with Einstein's predictions. Any modified theory that fails this test is immediately discarded. The challenge lies in constructing a model that is indistinguishable from relativity locally but slowly drifts away over billions of light years. Large-scale galaxy surveys are the key to testing these ideas. If gravity differs at cosmic distances, the way structures grow will also change. Some models predict faster growth, while others predict slower. Future missions are dedicated to measuring these growth patterns with extreme precision to capture those subtle fingerprints of deviation from Einstein's rulebook. Gravitational waves also offer a new frontier. In relativity, gravitational waves travel at the speed of light. Many modified theories predict slight changes in their speed or attenuation. In 2017, the observation of gravitational waves from a neutron star merger arriving almost simultaneously with its light confirmed that gravitational waves travel at the speed of light to an astonishing degree of accuracy. This immediately ruled out a vast number of modified theories. A more intriguing concept is massive gravity. In general relativity, the mediator of gravity, the graviton, is massless, allowing gravity's reach to extend infinitely. If the graviton possessed even a tiny mass, gravity would weaken over cosmic distances, potentially explaining expansion without dark energy. While the mathematics are incredibly complex, interest in this area is growing. Skeptics of modified gravity argue that dark energy, despite its mystery, remains the simpler explanation. Adding one new component allows us to keep the proven success of relativity. Conversely, modified gravity often requires complex new mathematical frameworks that can seem contrived. Following Occam's razor, science often leans toward the dark energy perspective. However, the cosmological constant itself carries deep perplexities. The vacuum energy predicted by quantum physics is so massive that for it to match reality, almost all of it must cancel out, leaving a tiny residue. It is like trying to balance a pencil vertically on its tip. Modified gravity offers an alternative, changing the rules of the game entirely. History shows that both paths can succeed. When Uranus's orbit was anomalous. Researchers proposed a new planet, Neptune, and they were right. When Mercury's perihelion shift didn't match Newtonian mechanics, the answer was not a hidden planet, but a new theory of gravity. Dark energy may be our Neptune, or it may be our Mercury. Only by pushing our theories to the limit will we know for sure. Einstein's equations have won every battle so far, but nature may still have surprises in store. The accelerating universe is exactly such a surprise, and whether it points toward an unseen energy or a new understanding of gravity remains one of the greatest unsolved mysteries of modern science. That concludes our knowledge sharing for today. I wish you all peaceful dreams and a wonderful day ahead. We will see you in the next episode.